a three-tier architecture, which is the most common architecture for web applications. In this architecture, the first layer is the presentation layer or the front end that uses HTML, CSS, JavaScript, or frameworks like React, Next, AngularJS, etc. And this is what the users see. Then we have the backend code, the backend layer, application layer, or business logic layer. Technologies used for that are Node.js, C#, .NET, Python, Django, and different languages with .NET framework. And then we have the data access layer or databases. And for that, we can use relational databases with SQL, different dialects of SQL, SQL Server, PL/SQL, MySQL, or NoSQL, and like MongoDB, things like that. So we have these three layers. They communicate with each other. The backend layer should communicate with the front end using APIs, especially RESTful APIs, and with the database using queries. So how do we develop a web application? First, we should design the UI UX, which should be converted into the front end, and then we should design database, which should be converted into the database code, into SQL code. And actually, some people design the database first and then design the UI UX. But the best practice is concurrent design. So we should design the UI UX and the database at the same time, iteratively, to make sure that they are consistent with each other. What I do is that I make a preliminary design for UI UX and then move to database, make the database design, complete the database design, and then switch back to UI UX, complete the UI UX, and then go back to database, finalize the design of the database, convert it to SQL, and then complete the SQL code, because part of the design, so the design continues in the code. So you may add procedures, triggers, functions, and you complete your design of the database. So the database should be informed by the design should be informed by the business logic. So you know the business logic, you make the designs for the UI UX database and also for the backend code, because many of your logic need to be implemented in the backend code. And I should mention that there are some applications that do not have a database. They just store, the backend code just stores the data in files. There are some applications that do not have a backend. The front end communicates with the database using just APIs and queries in the APIs. So they directly communicate with each other without a backend code. And there are some applications that do not have a front end. So essentially, they provide APIs. So they provide web service. And there are some applications that do not have the backend nor the database. They are just static websites. The static websites do not have, they just have the front end. And there are some applications that do not have backend, front end, or the database, like my AI application that helps you become a billionaire in 30 days. It does not exist. So it's an application without any of the parts. So the conceptual applications, the ideas that we have, yeah, so they don't have any of the parts. So here, I'm going to teach you an example, a very simple example, a bank that stores transactions. Who sent how much to whom? That's it. So we just store the transactions. And we keep track of the balances to make sure nobody spends the money that they don't have. So first, we make a preliminary UI UX design on Figma. So we go to Figma. So here we have the platform. So I'm assuming that you are familiar with Figma. And I first create a frame, mobile first. We just try to make it on mobile first, and then we can change it. And I'm going to make grid layout column, 6 columns would be good. And then we can add some buttons, actually some text boxes, etc. So it's going to take time. So probably we may not have enough time for that. So I have already made a design here. So I'm going to show you the design, the prototype. So the preliminary design should be something like this. We have to amount, send, and that's it, successful transaction. So it's a very simple prototype, and we have just the basic information here, and that's it. So it's gonna take like an hour. Just imagine that we spent an hour on this, and then the next day, the next day we are going to talk about databases. So the design of the database is the harder part, is the important part, and it's actually the core of your application. So how can we store the data in the database? So we should design the database. How can we store our data? One approach is that we store all the data in one table. So the table would be just like a spreadsheet. We have the information of the people and their balances, their addresses, and transactions for each person will be under the transaction column. By the way, when I say column, column is the same as variable, as field, as attribute, and row is the same as record unit. So they are equivalent. So in this table, what we have is that we have multiple transactions in each cell. And when we have like a person is involved in 1,000 transactions, it is going to be difficult to find a particular transaction for that person. So probably we need to have a table of transactions inside each cell. Essentially, we have a table of tables, and that is not efficient. It can cause many problems. In technical terms, we say that it is violating the first normal form. So to design a database, our database should comply with the first normal form. And that means we should have only one entry per cell. So for each column, for each variable, for each field, we should have only one entry. And we are not allowed to have unknown number of entries in a cell. So now our second attempt. Here we organize the data based on transactions. This way we have the transactions, the dates of transactions, sender, receiver, amount, and then the information about the sender and the information for the receiver. So we are complying with the first normal form. However, we are facing another problem. The other problem is that we are storing information for the receivers and senders multiple times. For example, if someone is involved in multiple transactions, we are storing their address multiple times. And this not only takes space, but also it can introduce anomalies like insertion anomaly, updation anomaly. So if we want to update this person's address, we have to update it everywhere in the database. And this is caused because of something called transitive dependency. The address depends on the receiver, and the receiver depends on the transaction. So the address does not depend on transaction. So the address is not specific to a transaction, but it is a transaction. It is a table of transactions. So this, essentially in technical terms, this is violating the third normal form. To have a normalized database, we have to comply with the third normal form. And that means we are not allowed to have transitive dependency. So what can we do? The best approach is to have multiple tables. We can have one table for the accounts or for people. We have account numbers and information about each account holder. And then we have another table for transactions. So we list the transactions here, and we don't need to put the information about the sender and receiver here. So we have just the account number of the sender and the account number of the receiver. And if we need to get information about the sender or the receiver, we just look them up in the accounts table. So now we are designing a database, and in the design process, I should mention that we don't care much about the contents of the tables. We care more about the variables or the columns and their types and their relationships. So what we do is that we use the design view for the database to design the database. And in the design view, the columns are actually, the rows are columns, and the columns are properties of the columns. So we have account is one of the columns. It is an integer. First name is text. So the types that I'm putting here are based on SQL Server, but if you use another dialect, you may use different types. They're very similar to each other. But we have the columns here, And there is one important notation here, PK. PK means primary key. And that means this column, account, is the primary key for this table. Every table must have a primary key. The primary key is the column that uniquely identifies every row in the table. It can uniquely identify every record in the table. So it should be unique for every record, and it should be universal. Every record should have it. No record can have it as null, and it should be stable. So it should not change very quickly, like balance changes, very frequently. So, so every table should have a PK. And I'm simplifying this table because just we want to simplify database. We cannot store the password here on the database. So instead of password, I use the public key. I store the public key. The user has the private key, and then we can verify that using the public key. So we should do the same thing with the transactions table. We see that in the design view, and we have the transaction ID as the primary key for this table. We also have some new notation, FK. FK means the foreign key. So these two columns are foreign keys. That means they point to primary key or primary keys in another table. Essentially, they are pointing to values in another table. Most of the time, foreign keys point to primary keys, but not always. So this essentially, the foreign key is just a constraint that limits the values that a column can take, the possible values. And this is good. We want to have as many constraints as possible in our database, because constraints prevent errors. We want to prevent errors. And foreign key is an important constraint that we can use in any database. So here we specify that we have two foreign keys. We know that they are pointing to the accounts table. However, in another database, we may have like 50 tables. So how can we specify which table they are pointing towards? So they're pointing towards the primary keys in which tables. So we have to specify those tables. Essentially, we have to connect the tables that relate to each other. To do that, we use Crowfoot notation. So the most important symbols are this, which means one record from the other table is associated with one record from this table. The next symbol means one record from the other table can be associated with multiple records from this table. These are called cardinality. And using the cardinality notations, we see that we can connect transactions to accounts, and we see sender can be one account in the accounts table. So each transaction can have one account as a sender. The same, each transaction can have one account as a receiver. On the other hand, an account can be the receiver in multiple transactions. An account can be the sender in multiple transactions. So when we see a relationship like this, you know for sure that when we have a foreign key, the other side of the foreign key should be one. And that is because of what? First normal form. So you know that the sender should be just one value. The sender should be one value. And since this is a foreign key, it is a one value from another table. And hence we have one here. And again, receiver just takes one value. It is one account from the accounts table. And that's it. We are establishing a one-to-many relationship like this. A record from one table can be associated with multiple records from the other table. So in addition to cardinality, we can also have ordinality. Ordinality specifies the minimum number of values can be associated with one record. So we can have one and only one, optional, at least one. This means at least one, and this means zero or many, so any number that you want. So this is ordinality and cardinality together. So using the complete Crowfoot notation, we can connect the transactions to accounts like this, and we see that sender is associated with an account, and a transactions is associated with one account and only one account as the sender, because of course a transaction must have a sender. But an account can be the sender in no transaction or multiple transactions. So it is possible an account does not send any money to anyone. so a stingy person does not send money to anybody, but it is possible that an account sends money to several people. So an account can be sender in multiple transactions, and the same is for receiver. An account can be receiver in multiple transactions or no transaction at all. So this way we established the relationship between these two tables. However, it is possible that you want to send money to somebody together. For example, you're paying rent. You're paying rent, so there are multiple senders and one receiver, one landlord. How can we fix that? How can we do that? So we have many-to-many relationship, very similar to one-to-many, many-to-many relationship, right? But yeah, so we put the foreign key of transactions here, foreign key sender here, right? No. First normal form, remember? First normal form. We cannot have many here, many entries here, many entries here. We can have only one entry. So the solution is that we use a bridge table, a table that helps us to connect two tables to establish a many-to-many relationship. It is two one-to-many relationships, essentially. So you should remember that this sign, this symbol, which looks like E or F, always goes to the foreign key. So it looks like F kind of, you see, like this. So it always goes to the foreign key in one-to-many relationships. This is on the foreign key side. So you should always remember that. And when we have a many-to-many relationship, the bridge table actually has all the foreign keys. So both foreign keys reside in the bridge table. So we have this. So both foreign keys reside in the bridge table. Both foreign keys reside in the bridge table. It's like a bridge between the two tables. And there is one thing missing here. By the way, how much time do I have? I lost track of time.
Yeah, so you have 5 more minutes.
5 more minutes, okay.
Yes.
So here, one thing is missing. We need a primary key. Every table must have a primary key. One approach is to have a surrogate primary key. We just create a new column as a surrogate primary key that is reasonable. The other approach is to use the foreign keys combined as the primary key. It is called the composite primary key. And that is also a good approach, especially we know that the combination of the foreign keys is always unique. The combination of the foreign keys in the bridge table is always unique because we must have only one foreign key associated with another foreign key in the bridge table. So we can do the same thing that we did with senders. With the receivers, we have a many-to-many relationship here also. And then we combine the senders and receivers into the parties table. How do we know if they're the sender or receiver? The amount. The amount can be positive or negative. If it is negative, that means they are receivers. If it is positive, that means they are senders. So this simplifies our database. I'm going to go to Lucidchart and show you how you can actually use Lucidchart to make these diagrams, and then we generate the code together. So after you create the ERD, entity relationship diagram, we call it an entity relationship diagram. After you create the ERD, you design the ERD, create an export, you select the dialect of interest, and then you have the SQL code that actually creates the tables for you. Copy to clipboard, and you have the code here. So if you want, you can go to my GitHub and see the complete code, but I'm going to just give you some overview of the code. So here, the create table just creates the accounts table. We define the columns here, straightforward. And for the blocks table also, we define the columns here. For the transactions table, we define the columns here. And I am adding indexes also for the columns. The primary key is always indexed, but we may want to index some other keys, some other columns to increase the speed. Indexing a column increases the speed for retrieving data. it decreases the speed when we are inserting data. So we should be careful when we use indexing. And we have also the parties table, the bridge table. I indexed 2 columns because it's important to access the information fast. So another thing that we may want to add that Lucidchart doesn't give us. So Lucidchart just gives us the definitions of the tables, but we may want to add some more important information, not more important, some important information to the code. For example, we may want to revoke access to update and delete from tables, public, so public cannot update or delete. Also, I am here revoking access to insert information into block and transactions into two tables so that they have to use procedures to insert information into the tables. And granting access, I'm granting access to the public to create accounts and to create entries to the parties table just later, so they can just create transactions later. And most importantly, I'm granting access to public to read any data that they want from any table. So this is a public bank. This is a transparent public bank that gives access to everybody. So we want to be public and transparent, and at the same time, completely 100% secure. So here I'm defining some triggers to prevent accessing information, unauthorized access. Here also, I'm preventing unauthorized access using triggers. So triggers is an important topic, but so it's more advanced. So I'm defining a function to get the balance of each person. So here I'm calculating the balance of each person using the function. So if we have a query here that calculates the balance of each person dynamically using the previous transactions. So based on the previous transactions, we calculate the balance. And here we confirm the calculated balance. And here another function, we calculate the transaction fee and etc. So we have another function there, a procedure here